Hi everyone, today I'm presenting on behalf of our team project, the UAlbany campus portal. Over the past semester, we have designed, developed and deployed a real-world web application that demonstrates modern security practices, accessibility standards, and responsive design. During the presentation, we will walk you through our application, the security vulnerabilities we identified, and the defensive strategies we implemented to protect user data and system integrity. The UAlbany campus portal is a full-stack web application that simulates a real social network platform. It is currently deployed live on render.com with both a front-end static site and dynamic backend. Users can register, create profiles, post content, comment, like posts, and interact with other students. This realistic application gives us a perfect test bed for discovering and addressing real security threats that exist in production applications. We build this application using industry standard technologies. The front end is distributed as a static site that is downloaded in users' browsers. The backend is a REST API running on Render's infrastructure. We use MySQL for persistent data storage, JWT tokens for stateless authentication, and multiple security libraries. This stack reflects what you would see in real startup application and enterprise environments. The key insight here is that security is not an add-on. It must be integrated from the ground up. The WASP Top 10 is a consensus list of the most critical web application security risks. We evaluated our application against each of these. Today, I'm going to focus on these threats most relevant to campus applications, like injection attacks, cross-site scripting, broken authentication, sensitive data exposure, and access control issues. Each of these has been extensively researched and documented. Our approach was to identify which threats apply to our specific application, implement defensive measures, and then validate that those measures work. SQL injection is one of the oldest and most dangerous web vulnerabilities. The attack works by inserting SQL code through user input fields. The attackers could type or 1 equals 1 into the login form, and if the backend was not properly protected, they had bypassed authentication completely. We prevent this using parameterized queries. The database driver handles escaping special characters, so SQL code cannot be injected. Every query in our application uses parameterized queries. You can see the difference on the slide. The vulnerability version concatenates user input directly into queries, while the secure version uses placeholders. In our application, every database interaction sanitizes input. Our backend receives requests from the front end, validates that the input matches expected patterns, example, email looks like an email, and then passes it to parameterized queries. The MySQL driver handles the rest. We tested this by attempting SQL injection attacks. They failed at the validation stage and never even reach the database. This defensive depth approach ensures that even if validation is bypassed somehow, the parameterized queries provide a second line of defense. Cross-site scripting attacks exploit the browser's ability to execute JavaScript. If an attacker can inject a script tag into your application, the code runs with full access to that user's session, including stored tokens. This is devastating because one user's compromise can lead to many accounts being hacked. We defend by escaping all user-generated content. This means converting special characters like those in the slide, so they are displayed as text rather than executed as code. Every post, comment, and user input in our system goes through this escaping function before being displayed. We tested cross-site scripting extensively by attempting to inject various scripts. Every attempt failed safely. The escaped HTML ensures that malicious code appears as plain text. Additionally, we implemented content security policy headers that tell the browser only load scripts from these sources. This creates multiple layers of defense. Even if somehow an attacker bypasses HTML escaping, the CSP would block unauthorized script execution. Broken authentication is when an attacker can impersonate other users. We prevent this with three key strategies. First, we use bcrypt.js to hash passwords with a computational cost. It takes time to verify, making brute force attacks impractical. Second, we use JWT tokens that expire after 7 days, forcing reauthentication. Third, tokens are stored in local storage where they are accessible to our application but isolated from other domains. In production system, we would also use HTTP-only cookies for even stronger protection. We tested authentication defenses. We tried to use stolen tokens, modified JWT payloads, and brute force passwords. All attempts failed. The hashing algorithm successfully slowed down password verification. Although we didn't implement rate limiting in this version, it's a recommended future enhancement that will reject excessive login attempts from the same IP. Course headers prevent a malicious website from making requests to our API on behalf of stolen credentials. HTTPS encrypts all data in transit. Without it, password and tokens could be intercepted. We enforce HTTPS on both front end and the back end. Render provides free SSL TSL certificates that auto-renew. Our backend reads database credentials from environment variables, not from code. These variables are set in render's dashboard, never exposed in source code. We also ensure that the EMV files are in gitignore, so they are never committed accidentally. We validated that no secrets appear in Git history, which is critical for security. We scanned our entire Git history for secrets, found none. We verified HTTPS is enforced by checking SSL TSL connection and headers. All database credentials are environment variables. The principle here is defense in depth. If one layer fails, others protect you. Even if someone accessed our GitHub repository, he could not find production credentials because they are only on Render's platform. Cross-site request forgery attacks tricks users into making unwanted requests to your application. For example, a malicious website could trick your browser into deleting all your posts. We prevent this with course headers that only allow requests from our legitimate front-end domain. When a malicious site tries to make a request, the browser blocks it because it is from a different origin. This is enforced by the browser itself, not our code, very robust. We tested cross-site request forgery by attempting requests from unauthorized origins. All attempts were blocked by our course configuration. The browser itself enforces this. The request never even reaches our backend. This is incredibly powerful because it protects all our endpoints without needing to add individual validation to each one. Security headers tell the browser what content is allowed. We configure them to prevent framing, clickjacking, MIME sniffing, and unauthorized script execution. Error handling is important. We log detailed errors server-side for debugging, but return generic messages to users. These prevent information disclosure. We also use environment variables to keep configurations separate from code. No application is 100% secure. We identified several areas for future improvement. Rate limiting will prevent automated attacks by limiting login attempts. More comprehensive logging would help detect attacks faster. We will benefit from automated security testing tools that can discover vulnerabilities at scale. The key takeaway is that security is an ongoing process, not a one time implementation. Phishing is fundamentally a social engineering attack, not a technical flaw. However, we defend by using HTTPS prominently. The lock icon gives users a visual confirmation they are on a legitimate encrypted connection. We designed our emails to always use full URLs so users can see the destination before clicking. We never ask users for passwords via email. While technical measures help, user education is equally important. Users should verify the domain before entering credentials. Denial of service attacks attempt to crash or overload systems. We rely on Render's infrastructure, which includes DDoS protection. Their platform autoscales to handle traffic spikes. At the application layer, we use connection pooling to ensure we don't exhaust the database resources. Rate limiting would be a valuable addition to prevent single user attacks. Render's monitoring tools allow us to detect unusual traffic patterns. Spamming is less about security breach and more about service abuse. An attacker could create many bot accounts and spam the platform. We prevent basing spam through authentication and input validation, but we lack robust defenses like CAPTCHA and reputation systems. For a production platform, we will add these features. The code examples shows how CAPTCHA and rate limiting can be implemented with popular libraries. Server-side attacks exploit backend logic flows. A classic flaw is trusting the client to claim authority. An attacker could modify client-side code to send the role admin in the request or manually craft a request that deletes other users' data. We defend by always verifying authorization server-side. The JWT token is cryptographically signed so the client can't forge it. We check wherever the authenticated user has permissions before executing sensitive operations. Every state-changing operation in our backend verifies authorization. When a user tries to delete a post, we check, does the authenticator user own this post? We extract the user identity from the JWT token, making it impossible to forge. This prevents one user from harming another user's data. All operations are also implicitly logged with the user ID via the authenticated request. We systematically tested each major threat category. Our defense is successfully protected against all tested attack scenarios. This doesn't mean the application is unhackable. Security is never absolute, but it demonstrates professionally implemented defensive practices consistent with the industry standards. Deployment security is as important as application security. Render handles much of the infrastructure security for us. HTTPS is automatic. Secrets are managed securely, and they provide built-in DDoS protection. However, we still need to configure our application correctly. Our node environment is set to production. Sensitive values are environment variables, and error responses are generic. This shared security model between platform features and application configuration creates a secure deployment. Security is not something IT ops handle alone. Developers have a critical role. We are responsible for writing code that validates input, verifies authorization, and handles errors securely. Meanwhile, the hosting platform provides infrastructure level protections. Both layers working together create a comprehensive security. This is why we chose Render. It freed us from managing servers and security patches, letting us focus on application security. This real example shows how small oversights create security gaps. Without this header, an attacker could upload a malicious file disguised as an image. Our consistent use of security headers prevents entire categories of attacks automatically. This is why using libraries like Helmet.js is so valuable. They apply defense best practices systematically. Over this project, we discovered that security requires applying multiple complementary strategies. No single technique is bulletproof. Parameterized queries stop SQL injection, but we also validate input format. Cores prevent CSRF, but we also verify authorization. This defense in depth approach means attackers must overcome multiple barriers. We also learn to default to secure settings. HTTPS is on, CORS is restrictive, and complex operations require explicit authorization. Security isn't random. Industry has identified best practices through decades of research. The WASP Top 10 distills the most critical risks. The NIST framework provides a systemic approach: identify threats, implement controls, test them, and respond to breaches. By following these frameworks, we are not inventing security from scratch, but building on proven methods. We performed extensive manual testing to validate our defenses. Automated security testing tools like OWASP Zap can scan for vulnerabilities at scale. We recommend that before any major deployment, a professional security firm performs penetration testing. They will try tactics our team might overlook, providing valuable feedback. During this short demo, I will point out few security indicators, show you the HTTPS lock and valid certificate. I encourage you to try our web app for yourself to create an account. I will highlight that the password is never sent as plain text. Create a social media post and attempt to inject HTML JavaScript. It renders as escape test. In developer tools, you can see the JWT token and check that it will be rejected if modified. Visit an endpoint without authentication to see the 401 unauthorized response. Query your own profile versus someone else to see authorization checks working. This application represents a solid foundation, but production grade security requires continuous improvement. We have outlined the roadmap for hardening the application further. Organizations building web applications should treat security as a core competency, not as an afterthought. Developers should be trained in secure coding, and budgets should allocate time for security work. It's not an optional. Security doesn't require advanced techniques or massive budget. It requires applying well-known practices consistently. We use standard libraries, Helmet, Bcrypt.js, standard protocols, HTTPS, JWT, and standard validation techniques. The result is an application that successfully defends against the most common web attacks. As you enter the technology field, remember that security is a selling point. Customers and organizations prefer application they can trust. Invest in learning security practices. Your future employers will value it, and your users will depend on it. We have covered the comprehensive security implementation of the UAlbany campus portal for threat identification through defense implementation and testing. The live application is available for you to test, and source code is available for code review. Our documentation goes into technical depth if you are interested in specific implementation details. We are happy to answer questions about any aspect of the security approach. Thank you for your attention.